For the rest of the section, let's talk about another concept. We are going to talk about lines, planes, and curves and surfaces in R3 in a space. Let's start with the simplest shape we can have in a space other than just a point, which is a line. Before I give you the definition, take some time to think, what information would you need to draw a line in space? To describe a line in space, we need a point and a direction. For example, a line that you are more familiar with would be a line in xy plane. And the equation of a line in xy plane in R2, we can write it as y equals the slope m times the independent variable x plus the y-intercept b. This form is also determined by a point and a direction. The point is determined by the y-intercept b, and the direction is determined by the slope or angle of inclination, the m. Similarly to a line in R3 in space. In a 3D space, a line is also determined by a point and a direction. We could use the point-slope form. Here's the illustration. Suppose I have a line L. Then if I give it a point in L, suppose this point, and I call this point P0. And I also give you a direction that is parallel to this line. Let's call this vector B. Then you could basically draw this line if I give you these two pieces of information. Suppose the point P0 in the line has coordinates of x0, y0, and z0. And the directional vector B has components of A, B, and C. Given that this vector is parallel to the line L, then from this two information, we are able to write out the equation of this line. Suppose an arbitrary point on this line has coordinates of x, y, and z. Then this equals a vector with components of a point on the line, which is from P0. So x0, y0, and z0. Then plus any scalar, let's call it t, times the directional vector A, B, and C. And the t here is called the parameter. So the p could be any real number. And the set of points x, y, and z with all the t's in real number, all the points would form this line, L. Or we can expand the vectors, and we write the vector x, y, and z as x0 plus t times A, and second component is y0 plus t times B, and the third component is z0 plus t times C. And this is called the vector equation of L. Or we can write out three equations for each of the components. So x equals x0 plus t times A, and y equals y0 plus t times B, and the third component, c equals c0 plus t times C. And this set of equations is called the parametric equations of the line L. Another form to describe a line is we could isolate the parameter t and equate the result. Since when we describe a point on the line, we substitute a t into the vector equation. So the t in the parameter equations have to be the same t, have to be the same value. So if we isolate for t, then the first equation we get x minus x0, then divided by A. So this equals to t, and that should equal to the t in the second equation for y. So if we isolate the t in y, we get y minus y0 divided by B. And similarly, that equals to the t in the third equation, which is c minus c0 divided by C. And this is another way to describe a line in space. And this equation is called the symmetric equation of line L. Let's look at an example of line in space before we move on and talk about the planes in space. We want to find the parametric equations and symmetric equations of the line that passes through points A and B. Then in part B, we are going to find the intersection point of this line with the xy plane. If we have a line in space, then it will intersect with the xy plane or any plane at only one point, except when the line is within the plane, then there are infinitely many intersection points. Or, if the line is parallel to the plane but not inside the plane, then in that case, there's no intersection point. But generally, if we have a line in a plane, then they will only have one intersection point. So let's start with part A. Let's find the parametric equations and symmetry equations of the line. To write out an equation of a line or to describe a line, we need a point that is on the line and a direction that is parallel to the line. The question only gives us 2 points, so we need to find a vector that is parallel to the line. If 2 points are given, then we can define a vector that points from point A to point B. Then this vector will be parallel to the line. So let's let vector B, the directional vector, be this vector, A to B. Then this equals 3 minus 2 as the first component, then negative 1 minus 4 as the second component, and the third component is 1 minus negative 3. So vector B has components of 1, negative 5, and 4. And let's take a point on the line P0 as point A with coordinates 2, 4, and negative 3. And of course, you could also take point B as the P0 since point B is also on the line. But if I take point A, then the parametric equations are x equals x0 would be the x coordinate of point P0, that is 2, then plus first component of the directional vector, which is 1 times t. Similarly with y and z, so y equals 4 minus 5 times t, and c equals negative 3 plus 4 times t. And the symmetric equations are when we isolate the t from the parametric equations and equate them, which are x minus 2 divided by 1 equals y minus 4 divided by negative 5, and that equals to z plus 3 divided by 4. Then in part B, we want to find the intersection point of the line with the xy plane. Xy plane is when the level c equals to 0. So to find the coordinate of the intersection point, we could substitute z equals to 0 to the third equation of the parametric equations and find the t, then substitute the t to the x and the y equations. Or we could simply substitute z equal to 0 into the symmetric equations. Then we get x minus 2 divided by 1 equals y minus 4 divided by negative 5. So this 2 remains the same, and that equals 3 over 4. Then we can find the x and y from this. So for x, I add 2 on both sides, and I get x equals 11 over 4. And for y, I multiply by negative 5 on both sides and then add 4, and I get y equals to 1 over 4. So the intersection point has coordinates of 11 over 4, 1 over 4, and 0. And that is the end of the lecture. So in this lecture, we learned that to describe a line in space, we need a point and a directional vector. In the next lecture, let's talk about equations of plane in a space.